So this is the last slide deck for the exam. It's all about planning and learning. So when we have a model, we want to learn, but when we don't have a model, we got to, wait, I said that wrong. If we don't have a model, we learn, and if we do have a model, we plan. So this is a pretty cool diagram of how updates happen and how far they differ from the actual exhaustive search. So for the most part, this entire class has been model-free, but in the end, we talk a little bit about model-based. So when we're talking about model-based approaches, we kind of have to learn the model, and that means we're going to learn the likelihood of arriving at a particular successive state and having a certain reward signal for a particular action taken at a certain state. We can then learn the model by acting in the actual model, by acting in the actual environment and then remembering those experiences to create our synthetic model. So we act, we learn, we plan, and then sometimes we can use direct RL from the environment to modify our value or policy. Simulated experiences from the model are only used to update the value function. Real experiences are always used to learn the model. We're always going to use those to update the model. We're never going to use the model's simulated experiences to modify itself. That's a bit weird. What else? That's about it from this side. What kind of structure would you like to use to represent a model? Up to you, as long as you can walk it properly. DynaQ is a basic implementation of that diagram that you just saw right there. Here we have an actual step happening in the environment, and then we have simulated experiences happening down here. They're basically the same equation, but they're coming from different places. Here we're stepping in, if you see part step C, it's taking that step in the actual environment, and then for that second simulated experience, it's deriving the reward and successive state from the model that we learn. Again, this diagram, DynaQ, and this are all the same idea in a sense. You have real experiences that help modify the policy as well as teach the model. The model can generate simulated experiences that also modify the policy. Real experiences can also, I already mentioned that. So you can try to use Dyna to solve a particular maze. It's pretty good, but if you don't have any planning steps, you kind of don't do much. You only take actual steps and learn, and that's not very effective. That's basically pure reinforcement learning, as we saw with our Q-learning implementations. So the more planning steps you take, the more you can learn about the environment without taking actual steps in it. So without planning, you probably learn one step per episode, but with planning, you can learn several steps per episode. And these are all steps that would be avoided in the actual environment. Challenges, yeah. So again, if you have a non-deterministic environment, learning is not as transferable. So to handle that, we have DynaQ Plus. It basically handles the non-determinism in the environment by basically pushing up the reward for states that haven't been visited in a while, and that helps us. Prioritize sweeping is also, it's very similar to prioritize experience replay. Yeah, that's exactly what I wanted. Yeah. Instead of randomly sampling, we use TD error to sample. Rollouts are great for sampling in the exploratory space. Their job is to basically produce estimates for a current state and for a given policy. A really great example that implements this is the MCTS algorithm. So MCTS has a very simple loop. Select a particular state, expand upon that state by exploring whatever actions are available at that space. Once I choose an action, I simulate a rollout or playthrough where I begin at that action, take that state, and then play the game or play the problem, whatever it's called, to a terminal state. Once I arrive at a terminal state, I back up the reward that I've received to intermediate nodes and save the information. So select, start at a node, pick one, expand that node, play out from that node, back up the return that you've experienced. So this is an example of what MCTS values may look like. These values indicate the received rewards from exploring that state, and then the denominator is the number of visits to that state. So UCB1 is the tree policy in this example. It's a good tree policy to use because it helps choose which node to select. And then your rollout policy is a separate one. Your rollout policy is what determines how you choose actions in your playthrough. So that's during the simulation step. Yeah, so an example question is like which leaf would be chosen. So that would be based on UCB1 because during the tree phase, you have to use the tree out policy to decide which node to pick. And then after that is a rollout. Yeah. Again, it's very expensive because you have to do this at every time step. Okay, I2A. So I2A is pretty cool. It has an imagination core that takes in a observation of a current state and then outputs an action based on the policy net as well. And then from there, it gives you subsequent observation and reward. This imagination core is embedded into an imagination future. So you provide an observation, and then the imagination cores work together in a chain to generate a trajectory of observations and rewards. So basically give one observation, and then you get the rest of the trajectory until a terminal state. That trajectory is then translated or rather encoded into a rollout encoding. And this imagination rollout module right here is basically put into a rollout encoder, and that becomes part of a model-based path. So a bunch of trajectories are fed a single observation, they're aggregated, and then they're used to modify a policy and a value function. That same observation may go down a path of a model-free network or pipeline where it also performs some computations to modify the policy and the value function. So I2A is pretty good. It does lots of planning problems pretty well. Like this example is Sokoban. Wait, is this Sokoban? It probably is, but basically the problem with Sokoban is that you got to move boxes into desired locations, so it's a bit of planning and acting, and I2A does that very well. Some performance metrics, and yeah. So highlight of this particular slide deck would probably be, I want to say MTS. I really liked MTS because I was able to implement it, but didn't turn out very useful. Maybe just this image. This graphic has been very, very meaningful to this course. I could say, or I could say the same about this one, but I don't know if I'd say I2A or MCTS would be the highlight of this slide deck. Probably, yeah, I guess I'd have to go with, actually, yeah, this might be it, yeah. We can have this one be our highlight, yeah. Yeah. Cool, so that just about wraps up my last slide deck for the exam. Hope you guys learned something. 272 was quite a blast. And I don't know where I'll be going next with my reinforcement learning journey, but it's been good. See you guys in the next one.